Hi, Assalamualaikum and a very good morning. So now we are in chapter 4, chemical bonding. And now we are in the subtopic of 4.3 orbital overlap and hybridization, part 2 of the video. So in this video, we're going to learn about the drawing and the explanation for the formation of the hybrid orbital in the central atom. So we have the sp hybrid orbital, sp2, sp3, sp3d, sp3d², and we're going to look about that using appropriate example. For the learning outcome of A and B, we have looked about that in the previous video, which is in part 1 of the video. So without any further ado, let us start with part 2 of the video first. So, hybridization theory. So what is meant by hybrid and what is hybridization? So hybridization, basically the idea of mixing two or more properties together. So you can imagine like a hybrid car. So hybrid car consists of a car that uses a fuel, petrol in order to move. Menggunakan petrol untuk bergerak. And at the same time, it uses the technology of electricity, which is a solar energy, in order to move the car. So when there is a production of hybrid car, where it uses both electric and fuel in order to make the vehicle. So hybridization in chemistry, it basically involves mixing as well. So mixing, pencampuran. So it's a mixing of two or more atomic orbital in an atom in order to form a new set of degenerate hybrid orbital. So degenerate here means we're going to produce a new hybrid orbital that is equal in energy. And the reason we are doing the hybridization is that it allows us so that the orientation that we're going to produce is more stable and are consistent with the observed molecular shape, which is aligned to the VSEPR theory. Okay, and that is the reason why we hybrid the orbital together to make it more stable and consistent with the observed molecular shape based on VSEPR. And the new atomic orbital produced in the hybridization process are called as the hybrid orbitals. So there are a few examples. First, we have the sp hybrid orbital. So for the sp hybrid orbital, it involves the mixing of one s orbital with one p orbital. And as a result, we're going to produce two sp hybrid orbital. And the electron pair that we're going to have is 2. And the shape here is consistent with the VSEPR. So since we have 2 electron pair, then the shape here going to be linear. So since we are having 2 sp, it means that sp here is referring to one lobe. Satu lekukan sp and then another sp here. So that is why we have 2 sp. And it is consistent with the VSEPR, which the name is linear. Okay, and you can also imagine it in terms of pin, macam chart. Okay, so let's say if you have s hybrid orbital. So s hybrid orbital, you have a yellow color pin, 1 liter. Okay, and then you mix it with 1 liter of the p orbital. So p orbital, maybe you can use blue color. Okay, 1 liter of the p orbital. Okay, so this one referring to p, and the yellow color here representing the s orbital. So when you mix both of them together, what we're going to produce is the new color. Okay, where the new color here will have a larger volume, which is 2 liter of the green color. And the green color here refer to the sp hybrid orbital. Okay, they are adalah sama energy and have the same color. Before this, they are coming from the different energy. But once they mix together, they're going to have a similar energies or degenerate orbital, which is known as the sp hybrid orbital. Okay, so in terms of orbital diagram, you can imagine that we mix s orbital with one of the p orbital. So s and p here, because p you know that we have 3 orientation, right? But we only take one of the p orbital in order to form sp hybrid orbital, and we have two of them. So sp on the left hand side, on the right hand side, and sp on the left hand side, and we have two orientation. Okay. Now we're going to look into another type of hybrid orbital, which is sp². So sp² happens when we mix s orbital with two of the p orbital. Okay, pasal p orbital ada tiga kan, tapi kita fokus kepada dua sahaja. So when we mix them together, what we're going to get is sp². Okay, and then we're going to have three orientation, 3 sp². So sp², sp², and then sp², and it needs to be consistent with the electron pair arrangement, in which we have three together, all of them. So when they have three electron pair, it refers to the shape of trigonal planar. So it needs to be consistent with the VSEPR, and it has an angle of 120 degrees. Next, we can also produce the hybrid orbital of sp³. So we can mix one of the s orbital, and then we have 1, 2, 3 p orbital. So when we mix all of them together, they're going to produce a new set of hybrid orbital which is similar in energy. Before this, diorang berbeza energy. Sekarang diorang energy yang sama. And they have sp³ hybrid orbital. The combination of 1 with 1, 2, 3. So it's going to be sp³, and then we're going to have 1, 2, 3, 4. 4 sp³. Seolah-olah macam 4 liter. Okay, and since we are talking about 4 sp³, then we have 4 electron pairs, and the 4 electron pairs refers to the tetrahedral electron pair arrangement. So the way that we're going to draw our hybrid orbital going to be consistent with the tetrahedral shape. So it's going to be sp³, and we're going to have sp³, and then we're going to have sp³, and then sp³. Okay, so you can put slight angle on the left hand side, or I can use the slight angle on the right hand side. Okay, as long as it is consistent with the tetrahedral shape. Next, we're going to produce sp³d. So this happens when we mix s orbital, three orientation of the p orbital, and then one of the orientation in the d orbital, because we know that they have 5 orientation, right? But we need to focus on 1, 2, 3, 4, and 5. And as a result, when we mix them together, we're going to produce 5 orientation, 1, 2, 3, 4, 5. So the name of the new hybrid orbital going to be sp³d, and then we're going to have 1, 2, 3, 4, 5. We have 5 orientation altogether. Okay, we cannot get sp4. Okay, this is not exist because we only have 3 p orbital. And as what you can see here, initially they have different energy. Tetapi lepas diorang dah mix, they're going to have equivalent energy, which is degenerate orbital. Okay, so when we have 5 sp3, so we are referring to 5 electron pair. And this 5 electron pair refers to the trigonal bipyramidal. So if you were to draw the VSEPR, you're going to get it to be something like this. 3 on the plane, and then we have 1 and down below, like a pyramid. Okay, and if you were to draw the hybrid orbital, you're going to draw 5 lobes. sp³d², sp³d², and then you have sp³d², sp³d², and then you have down here sp³d². Okay, so it is consistent with the trigonal bipyramidal here. And then the last hybrid orbital that we're going to learn is sp³d², which refers to the 6 electron pair. So this happens when we mix s3 of the p orbital and then 2 out of 5 d orbital here. So when we mix together, they're going to form hybrid orbital of sp³d². Pasal they involve dua, and then they involve tiga, and then one of them. So it's going to be sp³d². And then we have 1, 2, 3, 4, 5, 6. So 6 electron pair here refers to the octahedral, and as a result, we're going to have 6 lobes. So 1 sp³d², 2 sp³d², and then we have 2 on the left hand side. Okay, and then this, and then like this. Okay, so label every lobe with sp³d², and they are equivalent in energy. Alright, so this is the summary of the hybridization, and we are only talking about the central atom. Kita hanya belajar hybridization that happens in the central atom. So let's say type an electron pair sp, 1 dan 2, so we only have 2. So the shape going to be linear. So sp2 happens when we mix s and 2p orbital, sp2, so it refers to 3 electron pair, which is referring to the trigonal planar. So sp3 happens or terhasil daripada mixing of 1s orbital with 3p orbital. So it's going to be sp3, which have 4 lobes, which refers to the tetrahedral. So sp3d, 1s, 3p, and 1d. Okay, so it's going to be trigonal by pyramidal shape here. And then for sp3d2, it's going to consist of 6 electron pair, 1s orbital, 3p, and then 2d out of 5. Kita hanya fokus kepada 2 sahaja. So it's going to become sp3d2 with the shape of octahedral. Alright. And from here, we're going to learn about the overlapping of the hybrid orbital. Now we're going to look into the steps in determining the VSEPR, molecular polarity, as well as the hybrid orbital. So in order to determine the VSEPR, we need to follow this step number 1, 2, 3, and 4 as what we have learned in the subtopic of 4.2. So from the VSEPR, we can determine the polarity when we use the electronegativity as well as the bond dipole and determine whether it cancel out or not. And when it is not cancelled out, then the dipole moment is not equal to 0, then it is polar. So this is the idea of getting the polarity. And from here, you can continue from this step 1 to 7 in order to deduce the hybridization of the central atom, and then draw the orbital diagram to explain what is happening in the hybridization process. And then the last and not least, you can draw the hybrid orbital overlapping. So you can do step number 1 to step number 10 after you watch this video. However, if the question didn't ask about polarity, you can just use step number 1 until step number 4, and then you just skip 5, 6, and 7, where from number 4, you go straight away to number 8, 9, and 10. Okay, so there are 2 ways, whether you want to use 1 until 10, like this, or you can use 1, 2, 3, 4, and then directly 8, 9, and 10. Okay, so there are few ways depending on what the question are asking. So now let us look into step 1, 2, 3, 4, and then the green line here, 8, 9, and 10. So let us look into the example of CH4 here. So for the CH4, as mentioned, you need to start up with step 1 until 4 first in order to do the hybridization process. So step 1 until 4 is something that you have learned in the previous video. So find the total number of valence electron first, and then calculate the formal charge and ensure that the formal charge is 0, 0, 0, 0, and 0 here. And then from the drawing here, you need to determine the class of the molecule, which is AB4. So from the AB4, you know that the molecular shape going to be tetrahedral, and then they're going to have the VSEPR shape to be something like this, which with an angle of 109.5. So step 1 until 4, you need to do it as usual. And then for step number 8 here, you need to deduce the type of hybridization that occurs at the central atom. Kita hanya fokus kepada central atom for the hybrid orbital. So since our central atom has 1, 2, 3, 4, means that we have 4 bonding pair electron. And since we have 4, it means that we have sp3 hybridization. So you can refer to here electron pair 4 and then it refers to sp3. So we know that the sp3 hybrid orbital will have the shape to be something like this. So sp3, 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 and then they're going to have carbon. So the carbon hybrid orbital of sp3 here. Okay, and now we need to draw the orbital diagram for the central and terminal atom, and then we need to explain. So this can happen due to the overlapping of the central atom with the terminal atom. So for the carbon at the ground state, you know that carbon will have 6 electrons, right? So it will have a configuration of 1s2, 2s2, and then 2p2. Alright, and since we are talking about the valence electron, so we only going to focus on this part here. So we're going to have 2s2 and then 2p2. So when we draw the orbital diagram at the ground state, we're going to get 2s2 and then 2p2, something like this. However, if you look at here, you can only produce one sigma bond and then one sigma bond. So which is not quite as what we wanted, because our drawing using VSEPR is to be something like this, right? It has 1, 2, 3, and 4 sigma bond. But at our ground state, we only have 2 single bond. So what's going to happen here is that one of the electron in the 2s orbital, okay, so we have the ground state. Now we're going to focus on the excited state. Of 2s and 2p. So similarly to here, 2s and 2p. So in order for us to get 4 unpaired electron, one of the electron here need to be excited to the 2p orbital. So what they're going to happen is it's going to produce 1, 2, 3, and 4. So that they're going to have 4 electron pairs secara single. Okay, why this need to happen? Because we need to form 1, 2, 3, 4 sigma bond. So in the excited state, there are 4 unpaired electrons in the carbon atom. The 2s orbital and the 2p orbital will mix together to form 4 equivalent sp3 hybrid orbital. So tadi kita dah ada ground state, kita ada excited state, and now we're going to produce the hybridization state. So hybridization state means mula-mula they are on different energy. Diorang tidak bersambungan. Okay, but now we need to mix them together. Kita kena campurkan diorang sekali in order to produce an equivalent energy. And we're going to have sp3 here. So we have 1, 2, 3, 4 hybrid orbital. So we're going to get 1, 2, 3, and 4. And they are on the similar energy. So we have the sp3 hybrid orbital. Right? And then we have done with the central atom. Now we're going to focus on the terminal atom. So for the terminal atom, we know that our terminal atom going to be the hydrogen. Okay, so drawing going to be, so our terminal atom going to be the hydrogen, which is our carbon here, then hydrogen, 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 and then hydrogen. So just now we have drawn our hybrid orbital of carbon, which is at the center, sp3, sp3, and then we have sp3, and then we have sp3, okay, which is referring to carbon. But for our terminal atom, we're going to have hydrogen, and we have 4 of them together. So hydrogen will have the configuration of 1s1. So the orbital diagram going to be looking something like this. 1s, and then we have 4 of them together. So we have 4 hydrogen. So they're going to have 1, 2, 3, 4. 1s, 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 referring to 4 hydrogen. Okay, and this one hydrogen, one electron from the hydrogen can overlap with one of these together. Okay, similarly, this will overlap with this in order to form sigma bond. This will overlap with this in order to form sigma bond, and then this will overlap with this in order to produce the fourth sigma bond. Okay, and that is why we need to use the orbital diagram. And as what you can see here from the drawing of the carbon sp3, 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 sp3. So each sp3, as what you have looked here, we have 1, 2, 3, 4, right? So each orbital got 1 electron. So you can draw 1 electron here, 1 electron here, 1 electron here, and then 1 electron here. Okay, and it is overlapping with 1s orbital of the hydrogen, which is spherical in shape. So hydrogen, spherical in shape, and then the region of overlapping, they're going to have different direction. So we label it as hydrogen 1s orbital. On this side, we also have hydrogen 1s different direction. And then we have hydrogen 1s orbital in different direction. And similarly to here, okay? Hydrogen 1s orbital. So you draw it completely, yeah? And then in the region of intersection, you know that it is end-to-end overlapping. So pertindihan yang nyata. So it's going to form a sigma bond. Here going to form a sigma bond. Here going to form a sigma bond. And here going to form a sigma bond. So you can see that the drawing of CH, H, H, and H here will have also 4 sigma bond. And this is consistent with what you draw, which is like this. So you need to label the carbon at the center with the hybrid orbital with the terminal atom of hydrogen. Okay, now let us do another example, which is using water. So similarly for water, you need to find the total number of valence electron first. So when you draw the valence, when you calculated the valence electron, and then when you identify the class which is AB2E2, where you can get the band shape, and the structure that you're going to get is to be something like this. So basically you have 4 electron pair because you have AB2, E2. Dua bonding pair dan dua electron pair. So it's going to have 4 electron pair. And this 4 electron pair refers to sp3 hybridization. Okay. And from here, you know that your structure going to be something like this. 1, 2, 3, and then 4. So you're going to have sp3, 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 and then you have sp3 of the oxygen. Because the hybrid can only focus at the central atom. Alright, so step 1 until step 8, there's no problem. Now we're going to focus on step 9. So for step 9, we need to draw the orbital diagram for the central and the terminal atom. So our central atom going to be the oxygen. So oxygen will have 8 electrons. So it's going to have the configuration of 1s2, 2s2, and then 2p4. Okay, so in the ground state, the configuration going to be, okay, so we're going to focus on the valence electron only, which is 6 valence electron, 2s2, 2p4. And in the ground state, you're going to have your orbital diagram to be 2s and 2p here, which is 2s2, and then 2p4, 1, 2, 3, and 4. Alright, and for this reason, we doesn't have to promote our 1 electron to the other side here. Okay, we don't have to promote as before. Why? Because if you were to look at our Dewey structure, we're going to have 1 and 2 sigma bond. So 1 sigma bond, 1 sigma bond. So it came from the unpaired electron, So for that reason, we don't have any, we only have 2 possible unpaired electron, and then in order to form 2 sigma bond. So for that reason, we don't have to excite it as before. Okay, and for that reason, our ground state and our excited state going to be the same. Okay, sama sahaja. However, there's going to be a hybridization that occurs. So hybridization means we're going to mix one s orbital and then p orbital together. So what's going to happen here is that we're going to form 4 orientation, 1, 2, 3, 4, with a level of sp³. 1 s orbital, then 1, 2, 3 p orbital. So we're going to have 1, 2, 3, 4, 5, and 6. So 2 of them going to form a sigma bond, 1 with hydrogen and 1 with hydrogen, and 2 of them here will form lone pair. Another 2 here will form another lone pair. So you know that since they have an sp³ hybrid of oxygen, so you can draw it to be something like this. Oxygen, oxygen, and then like this, sp³, 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 and then sp³. And then our drawing H and H here with lone pair and lone pair. So this is based on VSEPR, and then this is our hybrid central atom of oxygen. So you're going to have two orientation going to have two electron, and then 2 of them going to have single electron. So the single electron, we try to make it consistent with our VSEPR. So single electron going to be here, single electron going to be here, and then 2 electron going to be here, and then 2 electron going to be here. So it is consistent with our hybrid orbital that we have drawn. 1 and 2, 1 and 2, and then sp³, 1 and 1. sp³, 1 and 1. Okay, and then for the hydrogen terminal atom, we're going to have 1 electron, right? So you're going to have 1 s orbital, and it's going to have a spherical shape, and it's going to overlap with the 1 single electron here in order to form sigma bond. So hydrogen 1s orbital, and then it's going to provide 1 electron in order to make a sigma bond. And since we have 2 hydrogen, so we can draw another one. So it's going to overlap on the other side here. So 1s hydrogen here. Okay, and this structure here is consistent with our VSEPR that we have drawn, which is single bond referring to a sigma, single bond referring to a sigma, and the lone pair here referring to the lone pair here, lone pair there referring to this lone pair here. So you know that this structure here is consistent and both of them are correct. And this is how you relate the VSEPR in order to predict the molecular shape, and then use the hybridization at the central atom as well as the orbital diagram in order to draw the overlapping of the hybrid orbital. Alright, so I think that's all for today's video. See you again some other time. Bye!